Here is section 4.4, and I want to talk about the average value of a function. Okay. Now actually this works whether the function is always positive or actually changes value or is negative, but I think the way to intuitively see it is to look at it as area and kind of see what's happening with this. So we define our average value of the function as let's see, and I don't think they don't give a notation. You know, I'm going to say, you know, f bar. Now I'm basing that in, like on statistics, when we take an average, you call that x bar. So I'm going to call this f bar for my average value of the function f, and on an interval. And so on that interval, we're going to take the width of that interval, 1 over b minus a, times the integral from a to b of f of x dx. Now, what the heck is this? Well, a great way to look at it is if f of x is greater than or equal to 0, then, you know, our picture of this situation is that, you know, so here's A, here's B. I need to exaggerate this a little more. There we go. So I exaggerate that thing a little more, and you know, if I shade this in, call that area A, then A is my definite integral from A to B of f of x dx. Okay, so that's the total area. But now I could ask, okay, could you draw me a rectangle with the same area that has that same width? Sure, that's easy. You know, how would I do that? Well, I'd take that same width and I'd go up here and I'd say, well, that has to be the area A, and here's A to B. Well, so what's this height? Well, what I know is area, and I'll call that height h. The area has to be h times b minus a. And so h has to be a divided by b minus a. Oh, okay, there's a, is that integral. So if we divide that definite integral by b minus a, we'll get a height, okay, a constant height of a rectangle that has exactly the same area as this thing up here. That makes sense for an average height of f, right? At least I think it does. And so that height, as we have it here, it's that 1 over b minus a, and then times the area, but the area is the integral from a to b of f of x dx. And so, you know, if, again, if I, you know, here's A, let's come down here a little more, there's A, there's B, and, you know, my function does something like that, then, you know, it seems reasonable that maybe my average height might be in here somewhere. And, well, you know, what have you kind of done? Well, you've gone up here and you've, you know, taken this extra area and you've put a little bit there and a little bit there to even this thing out and make a nice square. Okay, so that's the average value of f. It's just the area under f here divided by the width of the interval you're doing it on. And again, all you've done is you've said, oh, I want to come up with a rectangle that has that same width and that same area. So that area. And again, how would you do it? Well, I've got the area, I've got the width, I just need the height, solve for the height. But where did that area come from? It came from that integral right there. So there you go. There's the average value of f. So f bar is that. And all there is to it, so it's not really an amazingly deep sort of thing. It's just, hey, we knew this was area. That was the width of the area. We'll figure out the height. There you go. And we've got a rectangle. Okay, so that's average area. Now, what I kind of skipped over was the mean value theorem. And they kind of approach this average value from the mean value theorem for integrals. But actually, since the average value is a definition, it kind of points to the mean value theorem. The mean value theorem simply says, so mean value theorem, MVT, okay, mean value theorem. It simply says that we should be able to find a value of f. So if we take the integral from a to b of f of x dx, we should be able to find a value of f in there where c is between a and b such that this is true. Well, I may not be able to tell you where c is, but I can definitely tell you what that value of f is. F of c is equal to h. Okay, because if I divide both sides by the b minus a, I will get the average value. And that average value is just that h we talked about up here. You can look at it either way. You get the mean value theorem, and then the idea of kind of coming up with this average seems reasonable. But also, if you come up with the average, it seems reasonable that this mean value theorem ought to exist, because I can't imagine, right? This is just an intuitive sort of idea. I can't imagine that, say I've got a function like that and I find its average, right? Its average isn't going to be below it. Its average isn't going to be above it. It's going to have to go through it somewhere. And, if this is A and this is B, then actually any of those, and there's my height h, then any of these values of c here, so here's a c1, a c2, and a c3, any of those would work. Okay, but it seems reasonable that that height h has to hit the function somewhere, because otherwise I can't see it as the average height, right? It just, if it's up here, well, it's bigger than the height everywhere. How could that be the average? If it's down here, it's smaller than the height everywhere. How could that be the average? It seems like the average would have to be sometimes bigger, sometimes smaller. But if I've got a nice continuous function, then it's going to, if it's sometimes bigger, sometimes smaller, it's going to have to hit that straight line somewhere in there. Okay, so that's the mean value theorem. And from this definition of average, it just seems reasonable that mean value theorem would be there. And so we can find such a c between a and b that we could replace that definite integral with just a constant, right, or a multiple of the width. But that's really saying the same thing that the average value is saying. We could, if there is a way to replace that with just a constant times b minus a. Yeah, okay, good to know. All right, so there is average value.